a couple of videos ago, we learned that a function that is a mapping from the set x to the set y is invertible. Invertible if and only if, and I'll write that as a if with two f's, if and only if for every y, so let me write this down. For every, I'll do this in yellow. For every y that is a member of our codomain, there exists a unique and I'll make that a little bit bold, a unique x that is a member of our domain such that f of this x is equal to this y. So that's just saying that if I take my domain right here, that's x, and then I take a codomain here, that is y, we say that the function f is invertible. We say that the function f is invertible, and we know what invertibility means. It means that there's this other function called the inverse that can essentially, if you take that in composition with f, it's like taking the identity on x, or if you take f in composition with it, it's like taking the identity on y. And we've done that multiple times, so I won't repeat that there. We know what invertibility means, but we learned that if it's invertible if and only if for every y here, so you take any y here, any y that's a member of your codomain, there exists a unique x such that f of x is equal to that y. F of x is equal to, or let me write it this way. If this is an x, let's say that's an x naught, f of x naught would be equal to y. So this y would be equal to f of x naught. You apply the function here, it's going to map it to this point here. It wouldn't be invertible if you had this. If you had two members of x mapping here. That would break invertibility if you had this situation, because then you wouldn't have the unique condition. You have to have a unique x that maps to this thing. And what I just drew here with this other pink mapping, we don't have a unique x that maps to y. We have two x's that map to y. Now, based on what I just told you on that last video, what does this mean? If we have a unique x that maps to each y, that means that we have to have a one-to-one mapping, that f has to be 1-to-1. So let me write that. So another way of saying this is that f is 1-to-1, or injective. Injective. So if we have two guys mapping to the same y, that would break down this condition. We wouldn't be 1-to-1, and we couldn't say that there exists a unique x, a unique x solution to this equation right here. Now, the other part of this is that for every y, you could pick any y here, and you're going to there exists a unique x that maps to that. So I don't care. There cannot be some y here. Let's say that there's some y here, and no one maps to that. No one maps. If that's the case, then we don't have our conditions for invertibility. So that would be not invertible. So everything in y, every element of y has to be mapped to. All of these guys have to be mapped to, and they can only be mapped to by one of the elements of x. So everything here has to be mapped to by a unique guy. Now, in the last video, what did we call it when a function maps to every element of your codomain? So this every here, what is another way of saying that? That a function maps to every element of your codomain. Well, in the last video, I explained that that notion is called a surjective. Surjective, or on-to function. So the whole reason why I'm doing this video is because I really just want to restate this condition for invertibility in using the vocabulary that I introduced to you in the last video. So given that the statement for every y that's a member of our codomain, there exists a x that maps to it, we could just say that f is surjective. F is surjective. And then the fact is, if we just said that f is surjective, that means that everything here is mapped to, but it could be mapped to, maybe, this person right here could be mapped to by more than one. Surjective doesn't doesn't by itself make the condition that there's a unique mapping from a member of x to that element of y. So in order to get that, in order to satisfy the unique condition of this condition for invertibility, we have to say that f is also injective. Is injective. And obviously maybe the less formal terms for each of these, you could call this on to, and you could call this 1 to 1. So using the terminology that we learned in the last video, we can restate this condition for invertibility. We can say that a function that is a mapping from the domain x to the codomain y is invertible if and only if, I'll write it out, and only if f is both surjective and injective. Or we could have said that f is invertible if and only if f is onto, I can write that here, on to and 1 to 1. 1 to 1. And these are really just fancy ways of saying for every y in our codomain, there is a unique x that f maps to it. There isn't more than one, and every y does get mapped to.